This is going to be grade 11 mechanics, first session. We're going to discuss basic forces, things like equilibriums, things like resultants, and just how do we work these out, how do we put them together, and just some of the very basic maths that's involved with it. And it's not actually heavy, it's very simple. Let's just imagine for a moment. First of all, if I was going to say to you, take your bicycle and ride at 15 kilometers an hour. That's cool, no problem, we can do that. But if I say to you, ride at 15 kilometers an hour there, I'm telling you two pieces of information. What you're getting is you're getting the information, which is the velocity, the speed as we used to know it, and we're giving it a direction as well. Now that's important in physics because what we have to do is we have to differentiate between up and down and left, right and left. So what we've got to do is in everything we do, we're going to be giving it directions, right? If I'm pulling something up, I have to say that it's going up. If it's going to the left, then I have to say it's going to the left. That's critical because next year and future sort of things in physics, you're going to do more with directions, and it plays a bigger role in things like momentum and things like that. But just for the moment, let's just go and we say, right, we have got a vector, and a vector is defined as two pieces of information. So we've got a magnitude, which is how much, and we've got a direction, left, right, north, south, up, down, east, west, or it could even be at northeast. That's going to be at, if we say north is there, east is there, we're going to have northeast is going to be at a 45-degree angle. So we have to give the directions. Now, let's just think for a moment. If I am sitting here and I'm currently on a wheel with casters on it, so I can move, what am I going to do? I'm going to say, right, if I have somebody with a rope pulling me this way, then logically I'm going to move that way, aren't I? If somebody pulls me the other way, I'm going to be moving that way as well. If somebody puts a rope up there and pulls me, I'm going to start lifting out of my chair. If somebody pulls me down, I'm going to get squashed into my chair. So just let's think, we've got essentially only two directions. We've got this way, horizontally, and we've got vertically that we have to think about. Because we're going to put forces in those different directions. And when we get to equilibrium, we're going to look equilibrium this way and equilibrium that way. But before we get there, so what we've got is we've got the forces that are acting on me are going to cause me to do things. As I say, if you pull me that way, I'm going to go that way. Logically, you know that. If somebody pushes you, you're going to move in the direction that the force was exerted on you. In other words, the direction in which you were pushed. That's what you're going to be doing. So let's now just think for a second. If I had a force this way of, let's say somebody's pulling me this way, and they've got a force of 100 that way, and somebody's pulling this way with a force of 100, what am I going to do? I'm not going to move. The forces are equal. So I am sitting here in equilibrium. In other words, I'm going nowhere. I'm stationary. Very important thing that we get in our minds, that when we see the word equilibrium, or we have to work out something that is in equilibrium, that we know that it's not moving. There's no unbalanced force. The forces pulling me this way are equal to the forces pulling me in that direction. This is a critical part of the physics, because if, let's say, for example, somebody's pulling me that way with 100, and this way they're only pulling me with 50, then obviously I'm going to be going in this direction, aren't I? I'm going to be moving with the unbalanced force. And the unbalanced force, 100, I've got 50, so I've got 50 force going that way, which is going to pull me in that direction. That leads us to the next part of this whole problem, is that there's an imbalance of forces there. Imbalance of forces means we're not in equilibrium anymore. our equilibrium has been disturbed. Now, we're going to get to Newton's laws, but before we do that, let's just think about it in a logical format. Let's not go and take a law and then try and break it down. Let's look at what is happening. Because what we want to do is we want to develop together a set of recipes that we're going to use when we attack physics problems. Various kinds of physics problems. Each one's got its own recipe that we put down, and then we seek to find the missing bit to let us solve the problem. And you're going to find that in physics, essentially, that is what we do. We put down what we're given, and we look at the piece that we're not, and we solve for that piece. Now, back to our forces. If we've got a force that's not in balance, I'm going to be moving. We call that force a resultant force. Because what does it do? It has a resultant effect on me. I am going to move. That is the result of the unbalanced force, is I start to move. So all of these are actually very simple little math. They're not even mathematics. A lot of it's just basic arithmetic, especially when we're working in these two directions here. Similarly, imagine a rope pulling me up. Now, what is it holding? It's holding me, the mass, and what is my mass in a force? We translate it to a weight. So we turn around and we say the force down is mass times gravity, which is my mass times 9.8 meters per second squared, which is that little a, the acceleration due to gravity. So that is pulling me back towards the center of the earth. Another key concept that we've got to keep in mind as we move forward through Newton's laws and through the whole concept of mechanics. Now, what happens if the pull up is equal to the pull down? I'm not going to go anywhere, am I? Nope, I'm going to stay still. However, I'm not really going to be touching the chair. You could pull it out from underneath me because I'm being held up. Something's holding me up. So I'm in balance. There we go. I'm in equilibrium, aren't I? I am sitting in equilibrium with the force on top. What happens if somebody pulls me upwards with more than my weight? I'm going to go up, aren't I? Just like if you were holding a rock with a string. Well, let me take this. Here we go. Yeah, it is a soap on a rope. They're not yet extinct, apparently. What we've got here is we've got the force pulling up. That's my arm. My muscles are holding it up. And the weight pulling it down. Currently, we're not going anywhere. We're in equilibrium over here. Now, if I pull up with a force bigger than the one pulling down, my soap on a rope starts moving in a vertical direction. Similarly, if I'm holding it here and the down force is bigger than I can hold it, it's going to fall. That would be the case if we had a rock that we could just hold, and all of a sudden we can no longer hold it. The rock starts feeling heavier and it starts pulling you down. It means that there's an imbalance in the whole forces that we're going to be playing with. The next thing is that this concept of a free body diagram that we have to tune into. Now, the free body diagram in itself is where we take the truck, the bicycle, the hot air balloon, whatever you like, the train, the how train, where we take those and we represent them as a single dot. So what we're doing is we're taking the whole thing and we're saying, okay, we'll put you as a dot and we just draw the forces on you. That's very important because the basic reason is it just makes it simpler to look at, okay? It lets us understand how those forces interplay, and it lets us understand how they break down with each other. So what are we saying? We're saying here that in the sort of introductory process to this, we're going to be talking about the equilibrium, which means staying still. We're going to be talking about a resultant force, which essentially is a force that replaces all of the other forces that exist. So let's have a look at something quickly. Let's say, for example, we have got a body, and there's our body over there. Now we can have a force acting that way. We can have a force acting that way, and let's put in one there, and let's put in one there. Let's call this one 50 newtons over here. and let's call this one 30 newtons over there. Let's call the force up, I don't know, shall we call it 40 newtons? And let's call the force down 30 newtons as well. Let's have a look. What do we now do? We now break up our logic into two bits. We ask in the horizontal separately to the vertical. So we say to ourselves, let us look at what is happening in the horizontal section. And you can see, if you look at it, the force that way is more than the force that way. Which means what's going to happen? Yep, that. Because there is an imbalanced force. That is the resultant in the horizontal direction. So we've got a 50 minus 30, a 20 Newton force that way, and now vertically my pull up is more. So what do? I say, right, I therefore have a resultant upward force of 40 minus 30 of 10 newtons. Okay? In other words, that's what we look at. We look at which way is bigger than the other way. Right? Just to help us with the logic. Yes, we're going to get to the pluses and the minus signs of these things, but in the interim build-up, we need to build it up from a logic perspective. It's not going to help us if we do it from, yes, we must do this way, positive. We'll get to that point. So what have we got here? Well, we've got a force pulling this way of 20 and a force pulling me up of 10, which is kind of like this thing, isn't it? What is happening here? I'm now pulling along this way and lifting at the same time. Well, this thing, remember, is free to move. It can go anywhere. So what happens? Well, I'm pulling up, right? There I'm pulling up. This one's pulling. So it's going to move this way and up at the same time, which means it's going to start taking off. Simple as that. Now, how do we work out essentially the final resultant, which is the direction and the force that I'm essentially going to go? It's actually simple. It's a triangle. Logically, where do we want to go? Exactly as I did, right? We're pulling up and pulling this way. So we want to move off at that angle. Well, let's see what happens. You know that when we can add these, we add them like so. We add them nose to tail because they're two vectors. 10 newtons that way. So what have we got? We've got a triangle that looks like this. 20, 10, they happen to be newtons. They could be many other things, but they happen to be newtons. So what does that give us at the end of the day? It gives us a hypotenuse over there like that. Now, let's take, for example, we say, right, I'm going to color you in, and I'm going to call you my resultant. This is the resultant force of all of those forces. In other words, what is it doing? It's taking away all the others and combining it into one single force, which is the force, which is the net effect that the body is going to feel, i.e., my soap on a rope is going to go up and to the right. It's going to start moving off in that direction. Actually, how do we calculate the magnitude of the resultant? Well, once again, we've got that the resultant squared is going to be equal to 10 squared plus 20 squared, right? And if we work that out, put my glasses on, if we work it out, it's going to be, first of all, we've got 100. Let's do this. 100 plus 20 squared equals that. That's going to be 400 over there. So we've got r squared equal to 500. Therefore, r is going to be equal to, let's just take the square root of that, and we get 22.36. So that's the resultant. So I can replace that 50, that 30, the 40 and the 30. I can replace them all with one single force acting there. It's 22.36 newtons. But it's also acting, remember we said it's acting at an angle. What is the angle? Well, here's a little bit, it's basic trig. Well, you could use whichever you prefer. I generally just stick with tan being opposite over adjacent. So tan of theta is going to be equal to 10 over in this case 20. So tan theta is going to be equal to a half. Therefore, theta is going to be arctan of 0.5, and that's going to be shift tan 0.5 is going to be equal to 26,6 degrees. So my angle, 26,56 degrees. So what's going to happen to our soap on a rope? Well, essentially, it's going to go up. The force is going to be 22.36 newtons that way, and the angle it's going to go up at is going to be equal to 26,56 degrees. So what have we done? We've worked out the resultant. The resultant is what? It is the numerical addition of taking all to the right, subtracting to the left, taking all upwards and subtracting what's there, and seeing what we get. Let's take, for example, that we got a different set of forces, and let us say they looked a little bit like this. There perhaps, and over there perhaps. Let's take this as we had a force here of 50 newtons and a force down here of 35 newtons. That is the two forces. This is the force in the y, this is the force in the x. It's down and it's to the left. So what do? We once again put in our nose to tail, and then we change it to red just to keep it consistent over here. What have we got? We've got our resultant acting that way, which means this body that's here is going to be pulled down. And we do the same process, and the resultant is going to be equal to 50 squared plus 35 squared, and that's going to be to the power of a half, which is our square root, and we can go and we can work out what the number is. So it's going to be 50 equals that, plus 35 squared equals that, and then I'm going to put that all to the power of a half, and I get 61. And then the last thing we have to do is give an angle. So we say that theta is equal to the angle whose tangent is opposite over adjacent, which is, now always stand it there and look to the opposite. Find opposite for it first. I'll tell you later why we do that. It's because when we do components. So opposite is going to be 35 divided by 50. So the angle that we're going to get is going to be shift tan 35 divided by 50 is equal to 30. Do you know what? It's 34.99. I think we can call that 35 degrees. Okay. So this one is going to be moving down at 35 degrees and a force of 61. What have we done? We've replaced all of the forces with one single force that acts on that. That's where we sit with this, right? So we've got a resultant. What is the resultant? The resultant is that single force that is going to result in a movement. It's the resultant of all of the other forces. Essentially, it's when we've taken them all into account, it's the net force. That's what it really is. That's a critical concept, because when we get to Newton's laws, that force actually becomes what we call F net, and we use that in the MA calculations, mass times acceleration. In the next section, we're going to take forces at an angle now, and we're going to break them down. Exactly the same process and procedure. We are looking to find either an imbalance, or if we're told it's in equilibrium, we're going to say that they must be equal to each other in the vertical and the horizontal. Let's just before we move on to the next section, let's examine that. What did we say? We said if the vertical forces are in equilibrium, then what's pulling up must be equal to what's pulling down. Well, obviously, here we go, isn't it? What's pulling it down? It's weight. What's pulling it up? The tension in the string, which is me. I'm holding it in this position. It's imbalance. So the force pulling up must equal the force pulling down. Similarly, if someone's pulling me that way with 100 and someone's pulling me that way with 100, I am in perfect balance. I am in equilibrium horizontally and I'm in equilibrium vertically. That means me, I'm sitting exactly where I am at the moment. I'm not moving. I'm, so to speak, in equilibrium. There's no imbalance forces acting on me. I know I repeat this, but this is one of the key concepts in this entire essential system of mechanics, is understanding the concept of equilibrium and understanding the concept of an imbalance force, which is not equilibrium, so we're going to move. That's unfortunately where a lot of students seem to sort of get confused. So the quicker and the more we can sort of get our heads around the fact that equilibrium, not moving, and if I am moving, there's a resultant force on me. Okay, we're going to cover, as I say, we're going to break them down into components next. So that's going to be our next task.